And if you're on that side of things where you're thinking AI is the solution to every problem, then you're overestimating its utility and where we're at. However, on the other side of things, if you're a business of any size and operating at least some type of technology, and you think that AI can solve none of your problems, I think you're also mistaken.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Daniel Whitenack. He is a data scientist for SIL International, and today on the podcast we're going to be demystifying AI. Just before we get started today, I want to say a huge thank you to my sponsor, SafeGraph. So SafeGraph have actually been on the podcast before. If you go back to episode 38 or just look through the archives and look for an episode called Building Geospatial Truth Sets, you'll find out a lot more about them there. But if you haven't heard about them before, they're geospatial enthusiasts just like us, and they do an incredible job of curating points of interest data, foot traffic data, and building footprints. So data like this can be used for mapping population movement or competitive landscape analysis, or perhaps determining how many visitors a specific building receives. I believe they have somewhere around 7 million points of interest covering the US, Canada, and the UK. So if you're looking for this kind of data in those geographic regions, please check out SafeGraph. Just as a side note, if you're wondering what kind of analysis you can do with this data, or if you're looking for some inspiration, if you go along to their website, safegraph.com, they've got a tab there called the COVID-19 Toolkit. There's some really, really interesting dashboards there. I know we've probably all seen enough dashboards there, but these are worth looking at. Check it out. I also want to mention SafeGraph do a ton of work for the community. So there's something called the Data Consortium, and this is a community SafeGraph have built, and they offer their data as well as a ton of support free to academics. I'll put a link to a SafeGraph in the show notes just to make it a bit easier for you to find. Hi Daniel, welcome to the podcast. Today I really want to ask you a few questions around AI, machine learning, and deep learning. But I think before we dive into the conversation, perhaps you could just take the time to introduce yourself to the listeners and maybe explain how you got involved in AI.
Yeah, thank you so much for having me, Daniel. I'm really excited to be here and chat about these things, which is really my passion. Before I was a data scientist and AI type person, I actually started out my career in physics, in computational physics, studying many body theory of electrons and atoms and molecules scattering off of one another. In doing that, I developed a good amount of modeling and computer and math skills. Eventually, that helped me because when I went into industry, it was sort of the time of hype for data science before really the hype around AI. And so I got a job as a data scientist. And over the years, I've done various things like fraud detection and pricing optimization and analyzing comments on news posts and all sorts of things. Eventually, I got connected with my current organization, SIL International. And what I'm doing now is working on AI technology that benefits local language communities. So things like speech recognition for local languages or machine translation or different natural language processing techniques.
Thank you very much for sharing that with us. So you are not the typical podcast guest, at least for this podcast. Normally we focus on geospatial people that are embedded in the industry, people that are working on geospatial problems. But that's not you. And the reason I invited you on today is because you're a podcaster. So I thought this will be a really easy interview. And you have this sort of deep understanding of AI. And that's what I'm hoping you can help me and the audience with. So maybe we could start with just sort of a general understanding or a general definition of AI, and then move off and talk about machine learning and deep learning and how they fit together.
Yeah, sure. That would be wonderful. And I really think that this is some kind of the messaging that needs to get out there because you hear a lot of hype about AI without really knowing what it is. So the way I think about AI is in terms of functions. So what I mean by that is some people might have programmed before, some people might not have. But a function is simply, if you imagine I'm a function would be like you give me some input, I give you some output. Like you give me a number and I add one to it, and that's an add function or something like that. So you give me input and I do a transformation and get output. So functions have existed in software engineering for since the beginning of software engineering, but not all of them have been AI sort of functions. So most of the time in software engineering, what people do is they hand curate the logic associated with those functions. So if I want an add function or some math function, I write my function and I specify exactly what happens to the input, how it's transformed, and how I provide output. And all of that's hand curated by me, the human. What an AI or machine learning or deep learning function does is that instead of me as the programmer or as the developer specifying all of the logic of that function, what I do is I create a function that has some sort of internal parameters in it that I don't set. So I leave those as parameters that are actually set by the computer. And how they are set is by allowing the computer to do a sort of trial and error. And this is called training in AI. So an example would be like this. Let's say I wanted to create an AI function or an AI model that recognizes cats in images. I could write a function that says, if I see a certain color in the image, then classify the image as a cat. And I wouldn't specify maybe the exact color that I'm looking for because I want the computer to set this parameter. Okay, so I've defined my function, but now I need to train my model, or I need to fit that function or find that parameter. And so what I do is I have a whole bunch of images. Some of them are cats and some of them are not cats. And I test a first, I have the computer basically do kind of dumb trial and error to try a bunch of different colors and see which one gives me the best results for classifying cats. Now, obviously, that function wouldn't work very well because it only has one parameter, and computer vision is a quite complicated task. But ultimately, that's what is happening in any sort of AI or machine learning model. The really core of the technology is this idea that I'm going to let the computer, I'm going to run one function or one process that sets the parameters for a different function, which I use to actually do my task. Something like computer vision or machine translation or something like that.
So you mentioned an interesting term there, and that was training the algorithm. And I think you talked about training data. Could you talk a little bit about this? Because at the moment we're talking about finding cats in images, and I love this example because the internet is synonymous with cat images. So this is great. We're going to try and find all of the cats out there in the different images we find on the internet. We train the algorithm. So we have an algorithm and we train it. What does training data look like? What is good training data? What is bad training data if we're going to find cats in images?
Yeah, so training data really has to do with having samples with the kinds of inputs that you are expecting to see in actual production or in actual usage of the model, but paired with the expected outcome that you expect your model to produce. So in this case, in the case of cats and images, I would have a whole bunch of images, and then sort of paired with each of those images, I would have the correct label for those. So there'd be a bunch of labels that would say not cat, and then some would say cat. And so it's this combination of samples of the input along with known labels for that input that allows me to do the following. And this is very logical because we do this all the time as humans, right? If a child is learning what a cat is, you can show them a picture of not a cat and say not cat, and picture of a cat and say it is a cat. And then if you show them a bunch of those labeled examples, they'll eventually figure out which ones the cats are. So it's the same process in training where we have data that is labeled cat or not cat, and then we just make a random choice of the parameters in our model. It can be any initial choice of those parameters, and then we make predictions for all of those images based on our initial guess for what our parameters should be. Remember, inside of this AI function. And then we see how well did we did because we know all of the answers we should have got, right? We know all of the ones that are cats or not cats. And so maybe we got 60% right. And okay, well, let's change the parameters a little bit and recalculate all our predictions and see if we do better. The training process is just really doing that over and over and over and over. Computers are really good at repetitive tasks, right? And so that training is just doing that kind of large scale trial and error process over and over. And there are ways to speed it up and not just have it be brute force, but to kind of follow a optimal trajectory to the right answer. But ultimately, it's that sort of trial and error.
It's interesting that you talked about picking a or guessing which parameter was going to have the most impact, or starting with one and then letting the algorithm run on this training data set. I was always under the impression that when we had a training data set, we had labeled images of cats. We could say, here are all the cats, algorithm. You find the parameters which are common to all of them, and then run it against a larger data set. How far off the truth am I?
You're not far off the truth. I think I would phrase it differently. So, in some sense, people have this kind of idea that an AI is like, I put my laptop in the corner of the room and sprinkle some dust on it and like put a hard drive next to it with pictures of cats on it, right? And at some point it knows what the cats are. How I would phrase it is like we have this unparameterized function, meaning just a data transformation where we've specified the structure of that, but we don't know the right parameters like you're talking about. We don't know which ones we should use. And so what we need to have the computer do is figure out what are the right or optimal parameters to transform input images into output labels of cats. But we have to start somewhere. We could give the computer that structure and set the initial parameters as all zeros, or we could set the initial parameters as all random numbers, or some other scheme of setting those, and then let the computer iteratively go over the images and update the parameters. I think in that sense, it's some people think it's less structured than it is, but it's ultimately sort of parameter fitting is the name of the game in most cases. Now, there are some kind of unique AI research problems where that's not all of the case, but that the bulk of what we do is that.
How important is that initial parameter? I mean, I'm imagining anyway that as the algorithm runs, it'll get smarter and make better predictions, I guess. Is that initial parameter, is that just, it just needs some kind of seed to be able to run or start making these predictions based on? Or are we just trying to speed up the process? Like if we make better guesses at the start, does that mean it will have to use less compute to finish the task?
Yeah, the latter is definitely true. So it also depends on the complexity of the problem, but I would say the bulk of the AI that's done in industry right now uses the idea of transfer learning, and all that means is that let's say that you've trained a model to recognize dogs in images, right? And you already have all of your parameters for your dog model, and I want to recognize cats in images. Well, those two tasks are very similar, right? So why don't I just start with the parameter set that you found for your model rather than starting from some random seed? It makes much more sense because my task is very similar to yours. I would actually take the knowledge that you've already developed and your parameter set and maybe just sort of tweak it a bit. And that's going to be a lot more computationally favorable than always starting from scratch.
And is this what we refer to sometimes as pre-trained models or pre-trained algorithms?
That's correct. Yeah, pre-trained model just means that like those AI functions that I'm talking about, before all the parameters are set, they're not trained. And then after all the parameters are set, we would call that a pre-trained model. The jargon is maybe a little bit confusing with the pre because it more means before, but pre-trained just means before I even get to using it, it's already trained. I don't have to retrain or refit those parameters because they're already set.
So that kind of makes sense to me that I can use a model that's already good at solving a certain problem. If I come with a similar problem, then it makes sense that, at least in my mind, that I can use that existing model and perhaps tweak the parameters a little bit and give it another input. But are we talking about like a generic deep learning, machine learning algorithm that we just take down from the shelf, and the only difference between its use case or application is the parameters that we set and the training data set? Or are there a plethora of different algorithms that we can choose from?
Yeah, there's a whole host of different algorithms to choose from. And mostly researchers have come up with these different types of models, which we would call architectures, because in our continual effort to confuse people with jargon, we have a name for it. Architecture just means that it's a configuration of a neural network. And there's certain what we would call layers of a neural network that we sort of bolt together to create an architecture. And that whole thing bolted together is our neural network. And these different layers of the neural network, some are better at processing certain types of data than other ones. So, for example, image data is often processed with what's called convolutional layers. And the sort of short story on that is that, like when we look at an image, we often don't take in like the whole image at once. We sort of look at different parts of it, like, oh, there's a plane up here, and there's some edges down here that look like road stripes or something. And we're processing a lot of different information in different parts of the image. And so a convolutional layer actually convolves over the image with a kernel and looks at different parts of the image rather than the whole thing, always processing all of it at once. In the case of natural language processing, although you can use convolutional layers, often what's used is what's called recurrent layers, which look at a sequence of things. So if you imagine text is a sequence of words or characters, depending on how you break it up. And the order of that sequence matters, and the relationship between things in the sequence matters. And so utilizing a type of an architecture of a neural network made up of layers that process sequences of things is often useful in natural language processing. But there's a whole host of all sorts of things that people are trying that work better or worse in certain cases.
So you mentioned neural networks there. Is that a certain type of AI? And if so, does it belong in the deep learning side of things, or is it over in the machine learning side of things?
Great question. With a sort of maybe not satisfying answer, the world of this AI stuff has developed such that people are using the term AI and machine learning, deep learning in a whole host of various ways that have essentially made the distinctions between those terms somewhat hard to define. But I would say that, like on the machine learning side, many times what people think of are maybe models that have been used for quite some time that aren't neural networks, things like decision trees and random forests and naive Bayes and other things. Whereas on the deep learning side of things, most of the time people are working with neural network based architectures that are generally larger in scope. And one way to sort of think about these kind of traditional machine learning models as separate from the deep learning or neural network models is that traditionally people have been fitting models for a very long time. It's just in the past it was sort of important that you create that model in a way that maybe has more expert input. Like if I'm modeling text or something like that, maybe I have a special model that is really geared towards my understanding of how linguistics works and how text is related. Whereas in the deep learning world, the thought process is a bit different in the sense that, yeah, I sort of want to know what my input data looks like. But at the end of the day, I'm kind of creating this really big function with millions and millions of parameters that can model just about any sort of input to output relationship. And so it's less interpretable. It's more of a sort of black box versus on the other side of things in the traditional machine learning world, it's less of a black box because you kind of understand the structure of your model a little bit more.
Okay, so you talked about understanding the structure of the models more so when we think about machine learning and maybe less so when we think about deep learning. Are there any other sort of things that differentiate these two models, these two ways of approaching AI that we should be aware of?
Generally, machine learning models, like if I kind of go down to the very simplest of machine learning models, something based around like linear regression, I might have like two, three, four, five parameters. Something more robust, maybe I'm thinking of like random forest model or something like that. I have a good number of parameters, maybe hundreds or thousands. But then when I think of a deep learning model, as soon as you start adding in like convolutional layers or recurrent layers and your model sort of expands, then you're talking about millions or even billions of parameters. And so one distinction data wise is that if you're going to fit a model that has over a billion parameters, you're not going to do it with 100 images, right? It's just the scale is not right. So generally in the deep learning world where you have these larger models that have very many parameters, you need more data in order to properly fit those parameters. Whereas in the machine learning world, there's models like, for example, customer lifetime value models that are used in marketing and sales that require very, very, very little data to start working quite nicely. And so the scale is definitely different. Now, that doesn't mean that if you like don't have millions of images to train on, you can do nothing. Because again, remember, a lot of industry AI is built on this idea of pre-trained models and transfer learning. So I may only have 100 images in my data set, but if I could build on a model that's already been trained on, 10 million images, then I might be all right.
Like, I'm assuming then that deep learning requires significantly more compute. Can you give us an idea of the different needs there in terms of computing power for these two different ways of using AI?
There's two phases of AI work with a model. One is the training side, which we've talked about a little bit, which is this time when you fit all the parameters of your model. The next is inference, when you're making predictions. So you've already trained all the parameters. You're not retraining your parameters every time you make a prediction. You're just doing the inference part. And so the computational needs are slightly different in either one of those cases. So on the training side is often where for deep learning where specialized hardware comes into play and it's most crucial. And by specialized hardware, I'm basically meaning GPUs. So if you think about and kind of look into how neural networks are structured, basically at the very core of what's happening is a lot of matrix based operations. Graphical processing units or GPUs are really great at doing those sorts of operations. And so, for training one of these deep learning models, you basically need a one or more GPUs. And for very large models, it's kind of gotten to the point where you're not going to make an advancement if you don't have even like a cluster of these GPU enabled machines. So, like, if you want to beat the record on an object recognition benchmark, you're probably going to need some type of specialized hardware cluster, with many tens or hundreds of GPUs to train your model just because there's so much data. But for example, my group, we only have a handful of GPUs. We do have some that are on premise, and that's sufficient for our needs because we're not trying to break those benchmarks, and we're also utilizing these transfer learning techniques. So that's kind of the training side where you need the specialized hardware. On the inference side, it's sort of a mixed bag. For something like real-time processing, let's say you're trying to do real-time speech recognition or real-time image processing of some type, and you need the answer, like I give you an image and you need the answer in less than a second. You might still need specialized inference hardware, either a GPU or there's other processing units for inference like graph core units and other things that are able to keep up with the pace of real-time processing with a very, very large model. In other cases, for batch processing or otherwise, you can run many AI models. The inference side, you can run on a CPU. Now, there may be memory constraints and such because your model is 3 GB big and you need to load it into memory, but it's not as intensive on the inference side. And there's many models even that can be optimized and run on things like your phone or a Raspberry Pi or something like that and do very complicated operations like image recognition and computer vision tasks.
Thank you very much for walking us through that. So now that I think we have a little bit of an understanding of some of the differences between machine learning and deep learning, perhaps you could give us a few examples where it would be best to use machine learning or best to use deep learning, just so we can, have a more sort of concrete understanding between the different use cases for these.
Sure, it's a good question. And it probably also gets to the question of when you would also need to use either of them, right? In some cases, you might not need to use machine learning or deep learning. I think on that point, some use cases that people could have in mind are places in their business or in their work where one of two things are true, or one or both of two things are true. The first is there's a complicated transformation of data that needs to happen, and humans can't even really think of how that transformation would happen. An example of this would be like you can actually detect like mental health issues and various other like cardiac issues from sound, from a person's voice. Now, I don't even know how to do that as a human, but a computer can actually do that. One of these AI models can do that. So that's an example of like, that's something maybe even a human's not capable of because the transformation of the data is so outside of what we would think of. The second case is scale, right? So even if I can do something as a human, like I can recognize cats in images better than any computer, or as good as any computer, probably. But if you give me 2 million images and say, label all the cats, I'm going to get really tired, right? Depending on what deadline you give me, I might not be so happy. So even if that operation can be done by a human, maybe you want to automate that at the scale with a model. So those are two things to keep in mind when you're thinking of, well, is machine learning or deep learning a good choice to use? In terms of one or the other, I think a couple things are true. There are many cases where there's maybe two things that would motivate staying away from deep learning models. One is interpretability. So for certain industries, let's say financial or healthcare or something, there's a high burden or even a government regulation that you have to be able to explain and audit the decisions that you're making. And so if you want to do that and have a little bit more interpretability of how you made the decision, then maybe a more simple model might be what you're after. The other thing is performance, right? We already talked about in certain cases, there's going to be a lot of specialized hardware involved in an AI project. You may not have access to that. And of course, if a more simple model that can be trained on my laptop, a machine learning model of the more traditional sense, if that can solve my problem, then well, I shouldn't have my company spend $2 million on a specialized AI hardware cluster, right? Now, in other cases, like there's problems that really are solved by AI models that, to my knowledge, have not been solved in other ways. Those things that I've been talking about around recognizing health issues in audio or doing sort of certain computer vision tasks, or maybe very complicated sort of optimizations and other things. So there's a lot of problems that deep learning is really good at. A final note, just very quickly, is that another distinction that you might think about between the two in terms of the output that you're wanting is traditionally machine learning models are good at, like if we're thinking of the process of parts going through a manufacturing line and I'm trying to put a chip into a board or something like that. Traditional models are maybe good at like detecting edges, or like here's an edge and then I'm going to move over 3 centimeters and put in the chip. What I'm not doing is really like perception. Like here's the socket, I can put in the chip. So there's also a distinction with maybe the fidelity of the output of these models. If you're wanting to do more like the understanding or perception side of things, that's often what's associated with deep learning.
I just want to stay with it with deep learning just for a second there, because when you talk about it, and I think you used the word black box before, it sounds like we don't have control over what's happening inside the algorithm, right? We can't document the journey in terms of we put this data in and then we know exactly what happened in order for us to get the result. Do you think that's one of these things that's kind of holding the industry back from really taking advantage of this? Not being able to point to the thing that went wrong, the parameter that wasn't correct?
It's a really good question. I think that may be part of what's holding certain things back. However, I think there is a sort of large scale trend where two things are happening. One is people are researching and providing tools for interpretability of these models that help us understand, where they're biased and what features generally are causing the model to make certain decisions. So those tools are gradually increasing. The other thing that I think is really, from my perspective, the thing that's going to make maybe the most difference is that as an industry, we're getting better at testing our work. So, whereas I think we've been in sort of the wild west of AI for quite some time, where it's mostly scientists and data scientists, not software engineers doing this stuff, and they're doing it really around the idea of experiments, not production ready systems. Well, in production ready systems, when I'm using I have to have some way to test things. In software engineering, this sort of unit testing and CI CD, continuous integration technology has been developed and standardized over time to where there's really good best practices for making sure you understand how your software is going to behave before you put it into production. And I think we're making progress in terms of those sorts of techniques in the AI world, where we have things like adversarial attacks, which is a way to probe the behavior of your model. We have ideas like minimum viability testing, which helps you ensure that your model is behaving for many test cases in the way that you expect as the model is updated. And so there's various ways that people, I think, are being a bit more responsible in their AI development. And I'm hoping that that has a positive impact on how people perceive these things.
I think anytime you can put a bit of documentation around what you're doing and showing that we've run it through certain standardized tests, I think that really sort of helps with the transparency side of it. And then it sets some standards, right? Like, okay, it's been tested in this way. Great. And we decide as an industry, yes, we're happy with that. And then we can look at it and compare it to other things and say, does this meet spec kind of thing? I think that side of things will really help as well. Right at the start of the conversation, you talked about data science, and you said something like when it used to be really popular or there was a lot of hype around data science. When you think about AI and the deep learning algorithms, machine learning algorithms, where do you think we are in terms of the hype cycle?
Great question. Maybe I'll phrase it this way, which is often what I tell people. So I think for some time there was sort of the hype around AI and data science to some degree that like it's going to solve all of our problems, right? And if you're on that side of things where you're thinking AI is the solution to every problem, then you're overestimating its utility and where we're at. However, on the other side of things, if you're a business of any size and operating at least some type of technology, and you think that AI can solve none of your problems, I think you're also mistaken. So we're somewhere in the middle there, and I don't know that we've gotten to sort of, there's a bunch of terms around hype cycles and that sort of thing in terms of plateau and productivity. I don't think we're there yet, but I think we've gotten over some of that initial sort of unwarranted expectations. And we're getting more into the nitty gritty of how this can be a part of a new kind of layer in our software stack. And we're gradually, like I mentioned before, developing those best practices and those standards around testing and understanding the behavior of our models. And so I think we are on the way to that sort of plateau. And I think people should consider that if you're not thinking about it at all and you're sort of leading technology type things at your company, maybe you at least need to think about it a little bit. Maybe it doesn't need to be your main strategy, but you might want to spend some time thinking about it.
When you were talking there, I thought perhaps if I rephrase the question in another way, it'll help the listeners sort of understand where we are. And perhaps not talking about the hype cycle now, but as I understand it, there's three sort of broad categories of AI. We have narrow or weak AI, strong or general AI, and super intelligence. Could you tell us what each category, like give us an example of what each category might look like, and then perhaps tell us where we are in terms of those three categories?
Yeah, sure. So the sort of first area that you talked about with narrow methods is very much task specific, right? So I have a model maybe that does my spam detection for my inbox, and it's not going to do great spam detection for anybody else's inbox because it's fine tuned to mine, and it's not transferable in any sort of way in terms of how I can, retrain it and that sort of thing. There is a sort of middle area which is more generalizable, but not what we would call general intelligence or sort of super intelligence, maybe, where things are more transferable. So you see this happening right now, in my opinion, in areas like natural language processing and computer vision, where, like we were talking before, you can sort of reuse a lot of these general purpose models that Google and Facebook and others are creating for a whole variety of tasks. So there is this element of these models that are multitask and the knowledge is transferable to a variety of tasks. But it's not like, Facebook releases their model and then it sort of autonomously as a sentient thing learns how to do all sorts of other tasks. It's that they release a model that has some generalizable properties and developers, fine tune it for various purposes. That third category, which we would call AGI or general intelligence, there are people exploring this, and this would be kind of, I guess, the more Terminator like scenario where there's levels of, learning to learn and models kind of generalizing to a very many number of tasks on their own and having, very little distinctions between outputs from computers and outputs from humans. So that sort of sentient or singularity that people talk about of models sort of propagating in this way. It's interesting to think about that in an academic sense. I don't want to bash anybody that's doing that. As a practical person, I don't spend any time thinking about that. I don't personally think that, that's really something that will factor into at least our lifetimes. So I don't really think about it much. But if people like thinking about it, that's cool, and I'm all for it.
I'd like to try and round off the conversation now, but with a sort of a couple of quite general questions. So forgive me that they're not, really well encapsulated. But what do you think that the future, what do you think the next 5 years is going to look like in terms of progress with AI? Are there any sort of big sort of step changes on the horizon?
It's always hard to predict the future because I know I'll be wrong. A couple of the trends that I'm seeing, at least, are one that I already mentioned, just sort of best practices and more rigorous software engineering practices around AI and tooling that goes along with that. There's a whole world now called ML ops, or operations for machine learning, that is geared towards, training and tracking and versioning the things that we do. So I think that trend will continue. In terms of the models themselves, what I think is really interesting are maybe two fronts. One where we're actually looking at models that aren't so data specific. And what I mean by that is maybe not having text models or having image or video models or audio models, but having multimodal models that are actually able to take and fuse inputs from various modalities of data and do very interesting things with that. One example of this would be like removing background noise or something in audio. If you have a video of a person speaking and their audio, you can actually do really interesting things to trim out the background noise because you have the information from their lips, which makes sense because that's how we interact with people in a noisy environment. We look at their lips and what they're saying. So I think that'll be a trend that will continue. Lastly, I'm really interested to see there are a variety of kind of new types and architectures of models that people are exploring that are quite natively different than the models that we've been exploring for some time, like graph based models where we're not actually processing matrices internally, but we're processing graph structured things, which is very interesting in a variety of areas where we have very hierarchical data. Yeah, those are a few things on my mind.
So in the geospatial world, we often talk about that data fusion is perhaps one of the, is almost like the next gold rush. When we think about multimodal, are we actually talking about data fusion, or in your mind, are they two separate things?
It's a good question. I probably can't fully answer what's meant in many cases by data fusion in the geospatial world, but I think that in terms of, fusing feeds of data from various sensors and where there's a diversity of that data into a single model, I think that's what we would consider a multimodal model in AI, where again, like one of those cases where we have a video feed and an audio or a text feed coming together. And those are encoded into the same model rather than handled by two. Maybe a difference would be that what we're not talking about is having two different models for each type of data and then combining the data in a rule based way after that. We're talking about a single model that takes in both forms of data. And that's actually what we operate on in a joint way within the same model.
Daniel, not only do you have an amazing first name, but you've been an absolutely brilliant guest. I really, really appreciate your patience and your expertise. You managed to explain some really complex theories in a really easy to understandable way, and I really appreciate it. Where can the listeners go if they want to reach out to you or learn more from some of the work that you're doing, or perhaps connect with you?
Yeah, appreciate that. It's been fun for me as well. My co-host and I, Chris Benson, who's at Lockheed Martin, we do a podcast called Practical AI. So if you're interested in AI and podcasts, you can find us anywhere podcasts are released under the name Practical AI. You can find me on Twitter at dwhitena, and my website is datadan.io. And yeah, would love any listeners that want to reach out and have questions or connect. Happy to talk.
Thanks again for your time. I really enjoyed the conversation.
Same here.
Thanks again to my sponsor, Safegraph. If you're looking for points of interest data for the US, Canada, or the UK, check them out. Safegraph are geospatial enthusiasts just like us, and they do a pretty amazing job of curating points of interest data, building footprint data, and foot traffic data. So all the processing is done for you. This data is analysis ready. And of course, there's a bunch of different things you can do with it. They have a whole lot of examples on the website, so if you're looking for some inspiration for what you can do with points of interest data, go along to safegraph.com. I'll put a link to them in the show notes just to make it a bit easier to find. So I really hope you enjoyed that conversation between myself and Daniel Whitenack. I hope you now know a little bit more about AI, machine learning, and deep learning, and perhaps you even understand where and when to use the different acronyms. I think that in itself would be a big step forward for a lot of us. I am constantly amazed by people like Daniel that are really great at taking very complicated concepts and condensing them down into something that I can understand, something that people like us can understand. And I think this is a really underrated skill. And the pushback I hear on this sometimes is this idea that we're dumbing things down. And there's almost a fear that if we do that, then we're somehow going to misrepresent all of the facts. But I don't see it as dumbing down or misrepresentation. I see it as having empathy for the people that we are seeking to serve. So they might not need to know everything there is to know about machine learning. They need someone to filter for them. They need someone to show up and say, this is the summary that you need. This is the executive summary. And do it in such a way that they get the information that they need to make the decision that you're asking them to make. So if you're in the business of trying to persuade people to take an action, then you're also in the business of creating tension around that action. And the tension might be, this could be better. We have an opportunity here. There is another way. But we don't get to create that kind of tension. We don't get to try out our ideas and test things that might not work if we can't clearly communicate what it is that we're doing. And not just clearly communicate it in a way that we understand it, the people in the industry understand it, but clearly communicate it in such a way that the people that we're seeking to serve understand it. So I am clearly not an expert in AI, and I'm sure you will have picked that up from the conversation. My job is not to be an expert. My job is to be curious, to ask questions. But what if you're talking with someone who's not curious, who's not asking questions? What if you're talking with someone who's already suffering from decision fatigue? I think in that situation, the easiest thing to do is just to say, no thanks, this is not for me. But that no thanks, that might mean that you don't get to try out your idea. It might mean that you don't get to do interesting work. It might mean that we don't get to make things better by making better things. It might also mean that person, that they don't get to where they were trying to go because we were unable to create tension, because we were unable to communicate. I guess my message here is that next time you find yourself in a position where you need to communicate a technical concept to perhaps a less technical audience or an audience outside of our industry, I hope that you'll take the time to explain things in such a way that they can understand it. And I hope that you will see this as a generous act and not simply pandering to the lowest common denominator. Okay, that's it from me. Thank you so much for tuning in again this week. It's been an absolute pleasure bringing you this episode. As always, you're more than welcome to reach out to me on social media. I'm most active on Twitter and LinkedIn. My email address is info@mapscaping.com, so you are more than welcome to send me an email if you'd rather communicate that way. And that's it for another episode of the Mapscaping podcast. I'll be back again next week. We'll talk then. Bye.